It's a great pleasure to just quickly introduce this university lecturer, Sean Sullivan, who of course is the director of the Earth Institute, the Lamont-Doherty, and I just want to say, as I said, just a few things. First of all, the university lecture. I mean, this is something that is really, it's the ideal of what the university is all about. We come, we listen to each other, and we're fortunate to have such very, very distinguished faculty who know extremely interesting things, and that certainly is true of tonight. So for this decades-old institution, we should always be thankful. The second thing is that I'm really proud of Lamont-Doherty, and this is a gem within the university and within the broader world for the study of the Earth. And all the things that happen out there are part of what we want to bring to the bigger world, and that is done through a variety of ways, but not least through the Earth Institute. So Lamont-Doherty is a gem. And the third thing is to thank Sean for this lecture, but for being here. Every place I go, people speak in the highest possible terms about his work and about him as a person. And of course, he has very, very great honors, including the National Medal of Science. And we are really thrilled to have you here, Sean, and very pleased to have this lecture. John Coatsworth, Provost.
Good evening. It's my great pleasure to introduce tonight's speaker, Sean Sullivan. Pardon me. Director of the Lamont-Doherty Earth Observatory, Associate Director for Earth System Science of the Earth Institute, and the William B. Ransford Professor of Earth and Planetary Science here at Columbia. This evening, Professor Solomon will discuss the MESSENGER mission to Mercury, of which he is principal investigator, and help us to investigate a consequential question: why we explore the solar system. I had thought, as we were discussing earlier, that he was devoting his life to this project in order to provide academic administrators a very fast way to get out of town and a distant address to hole up in. But no, he has a scientific purpose. There are few better suited to guide us through a discussion of the meaning and purpose of planetary exploration than Professor Solomon, a world-renowned scientist who has studied the composition of the Earth as well as what lies beyond our atmosphere. Sean Sullivan grew up in Los Angeles, the child of two New Yorkers. As a budding scientist, he was first fascinated by dinosaurs and imagined uncovering the mysteries of the Earth's past through paleontology. His interests shifted when, as an undergraduate student at the California Institute of Technology in 1965, he watched a broadcast of photographs from the Mariner 4 mission that flew past Mars. His course may have changed, but that desire to explore and uncover the world's mysteries has endured. Professor Solomon completed his PhD in geophysics at the Massachusetts Institute of Technology, where he then taught and conducted research for almost 20 years. At MIT, he ran one of the earliest ocean bottom seismometer labs, and its observations greatly enhanced our understanding of the Earth's tectonic plates. Professor Solomon has led or been involved in a number of space missions to planets in the inner solar system, including the Magellan mission to Venus, the Mars Global Surveyor mission, and the Grail mission to the Moon. Prior to joining Columbia in 2012, Professor Solomon was a research scientist and director of the Carnegie Institution in Washington, and there he also served on the Executive Council of the NASA Astrobiology Institute, a body that seeks to determine how life originated and whether it might exist elsewhere in the universe. As I mentioned, Professor Solomon is also primary investigator on the MESSENGER mission to Mercury, which has made revolutionary contributions to our understanding of the closest planet to our sun. In this role, Professor Solomon is lead scientist as well as director of all aspects of the mission, from its conception, staffing, and funding to the final publication of the results. Among its many discoveries, MESSENGER has confirmed and photographed water ice on Mercury's poles, something scientists hope will lead to future insights into how our solar system was formed. Professor Solomon is a member of both the National Academy of Sciences and the American Academy of Arts and Sciences. And last month, President Obama presented him with the National Medal of Science, the nation's highest honor for scientific achievement and leadership. On Columbia's Palisades campus, Professor Solomon is as likely to be found in a seminar taking notes and posing detailed questions to the speaker as he is to be found behind his desk in his office. A dedicated advisor and mentor, he has made it his priority to ensure that the graduate students and researchers at Lamont-Doherty have the tools they need to succeed. Under his leadership, students and researchers are making precisely the critical observations and pioneering discoveries that will shape our understanding of our planet and ensure a sustainable and resilient future for the Earth and all human life. Please join me in welcoming tonight's university lecturer, Professor Sean Solomon.
Thank you, Lee, and thank you, John. I'm delighted to join you on a rainy evening in New York City to talk a little bit about why we explore the solar system, and in particular, why, other than sending university administrators, we might wish to explore the planet Mercury. One of the easiest answers I can give for why I'm interested in exploring the planets is this one, that we live on a planet, that our planet is 4.5 billion years old and was born by processes that also led to the formation of Earth's sister planets, the rocky inner planets, Mercury, Venus, and Mars. The outcomes of the 4 experiments in rocky planets are very different, and yet we know that the starting conditions were more similar. The laws governing planetary evolution should be common to all of the planets. And so I've always argued that to claim that we understand our own planet demands that we understand our planetary neighbors and the reasons for the different outcomes of the different experiments in our solar system, and as we're learning from astronomers around many other stars as well. So, to understand what made our planet special, we really need to explore and study in depth other planets. We could go to the planet Mars, one of our nearest neighbors. This is an image, of course, from the Curiosity rover, which filled the pages of the Science Times today. This rover has been on the surface of Mars since the summer of 2012, and it's exploring this giant mountain, more than 5 kilometers tall, made of layered sedimentary rocks in the middle of an impact basin, informally known as Mount Sharp. Mars once had a more extensive atmosphere. Mars once had water on its surface, running water, possibly lakes in the case of this impact crater and elsewhere, and is an illustration of how an Earth-like planet can start out with more Earth-like conditions and evolve to a dry, cold desert, not unlike the dry valleys of Antarctica. We could go to our nearest neighbor, Venus, which is the closest to our own planet in terms of mass. It's got an atmosphere of mostly carbon dioxide that's 90 times as massive as that of the Earth, and it's experienced a runaway greenhouse and climate change of the sort to dwarf anything that we talk about on the Earth. It has rocks that look like the rocks of the Earth insofar as we can sense them. It has huge volcanoes like this one, Mat Mons. This is, by the way, a false color rendering of a radar image taken with an imaginary perspective and a vertical exaggeration of 22:1. But otherwise, this is just like what it would seem if you were on the surface. And it is quite possible that this volcano and the areas around it are volcanically active today on the basis of measurements being made by European Space Agency satellite in orbit around Venus now. And I think many of you have followed the exploration of this comet 67P, again by the European Space Agency, and know that one of the reasons we go to comets is because they are remnants of the outermost solar system. They record some of the evidence for the earliest solidification of ices and other compounds that are easily removed at high temperatures, so-called volatile compounds, that occasionally are knocked into the inner solar system by a passing body like this comet here, a periodic comet, and that 4 weeks ago saw the European Space Agency plant the first lander on the surface of a comet nucleus. So those are all worthy and, in fact, ongoing targets of exploration of the solar system that would all help inform our understanding of the origin and evolution of our own planet and why the outcome of planetary evolution in the case of Earth differed from those of its neighbors. But we chose to go to the planet Mercury almost 20 years ago in a proposal to NASA. And the argument we made was in part this one, that Mars, Venus, and by now comets have been the subject of many, many space missions. And this is a list just of the ones that worked successfully. And only 2 spacecraft have been to Mercury. And one of those was in the 1970s, and the second one was ours. And so simply on the grounds that to go to a new place and to make new measurements it provides more opportunity for discovery than going to a place that's been visited already by 35 spacecraft, I think is one compelling reason to consider a visit to another of Earth's sister planets, but one that is comparatively unstudied. But there are 2 good reasons why it took more than 30 years between the first spacecraft that flew by Mercury and the Messenger mission, which was the first to orbit Mercury. And they're illustrated here on this list. It's hard to get into orbit. You have to slow down by a great deal, what the engineers call delta V, the amount of speed you have to reduce your spacecraft. And once you're there, you're close to the sun. And the day-side surface of Mercury is extraordinarily hot. And those 2 aspects of the environment must be dealt with by thermal design. And so the challenges to engineering of slowing down at Mercury as you're approaching the sun and gaining speed and surviving that close to the sun kept any spacefaring organization from mounting a Mercury orbiter for decades. The way we got to Mercury was quite complicated. And it was complicated to address the necessary change in velocity. And don't worry about the details, just appreciate this is a complicated slide. Looking down on the plane of Earth's orbit from the North Pole of the celestial sphere, you see that Messenger had to travel 15 times around the sun. It had to fly by the Earth once, Venus twice, and Mercury 3 times before at the, I guess I don't want to use this because I can't show both of these at once. There's a timeline at the bottom of the slide for those looking here, showing the time between all the flybys with propulsive maneuvers in between each of the flybys. It was complicated, but to try to picture how complicated it was. Imagine that you are playing billiards, and your billiard table is 3-dimensional instead of 2-dimensional, and your billiard table is about 200 million miles across. And you've got to shoot your ball to within 1 part in 200 million or so, probably half a part in within 200 million, 6 different times in order to make it to your target at the end. And that's the challenge that some very clever mission design people have to face in order to use the flybys of the inner planets to slow down the trajectory of a spacecraft enough so that it can be placed in orbit around the innermost planet. The rest of the design of the Messenger spacecraft was a challenge to engineers and a triumph, really, of engineering, particularly thermal engineering, mechanical engineering, propulsion engineering, communication engineering. The spacecraft had to be made extremely lightweight in order that it could be mostly propellant at the time of launch. It had to survive the high temperatures near the sun. It had to operate solar arrays at those high temperatures. And it had to operate in a range of temperatures in night side of Mercury. And some of the elements of the design are illustrated on this slide. Suffice it to say that the engineers involved, who were primarily at the Johns Hopkins University Applied Physics Laboratory, rose to the occasion. It was really a life-culminating moment for the thermal engineers, who never had as challenging a mission as they did with Messenger to come up with solutions that satisfied all of the extreme hazards and environments. But let me turn to the science, because we went to Mercury to solve some questions, and I only have time to talk about 3 of them. But let me explain why these 3 questions are interesting, why they are relevant to our own planet, and why we were able to make progress on answering those questions from observations made in orbit around the innermost planet. So the first of the 3 is, what is the composition of Mercury's surface? What is it made of? There were no measurements of Mercury's surface material before Messenger. We have no samples, unlike Mars and the Moon. We have no samples of this planet in our collection of meteorites. There should be meteorites from Mercury. It's energetically feasible, but none have been identified to date. So the issue is this. We've known for many, many decades that Mercury is the densest of the planets when you correct for the effects of internal compression, the effects of pressure. It's made out of the densest material, if you could compare it at standard temperature and pressure. And the only element that's common in the solar system and dense is iron. So it has been inferred for a long time that Mercury is mostly iron, and the presumption, by analogy with the Earth and secondarily with Mars, is that iron is in a central metallic core inside Mercury. But it's a much higher fraction of the planet than any other, and theoreticians have wrestled with the question for years as to why Mercury ended up so dense, so metal-rich. And one of these ideas is depicted in this artist's rendition of a giant impact that hit Mercury, a Mercury that was maybe the composition of Mars, but the impactor was almost the same size as Mercury. And the result was to almost disrupt the planet, but remove 3/4 of the silicate fraction, eject it into space where it was lost from Mercury's orbit, and leave behind a planetary core and a thin shell of silicate material. There are other ideas that are in the literature. All of them, before our mission, made predictions for the chemistry of what we'd see at Mercury's surface. So it was classic hypothesis testing, classic scientific method. In particular, all of them made this prediction on the bottom line here, that elements easily removed at high temperature, the so-called volatile elements, should be depleted in Mercury. And by volatile elements, I mean alkali metals, halogens, sulfur, elements that are depleted in the Earth's moon, and were predicted to be depleted in Mercury. So if we could measure these elements, we could test these hypotheses. So we took 2 instruments. One was an X-ray spectrometer, and that just measures X-rays coming off the planet. Mercury doesn't have much of an atmosphere. The sun is a great source of X-rays. The X-rays that hit the planet interact with surface material. The material fluoresces at X-ray wavelengths. You measure the energy of the X-rays coming off the planet. You can determine the composition of the atoms that are fluorescing. The second tool we used was gamma ray spectroscopy. This is higher energy photons than X-rays, produced by 2 processes. One is the natural decay of radioactive elements. 3 of them are sufficiently abundant to produce gamma rays we can measure. That's thorium, uranium, and potassium. But all of the other, many of the other elements produce gamma rays through secondary reactions with neutrons that are created as a result of bombardment of Mercury by cosmic rays. So cosmic rays generate a cloud of neutrons around Mercury, and many of those neutrons interact with other atoms, which then give off diagnostic gamma rays. So those are the two tools. I'm not sure why it doesn't look crisp from here. Anyway, the very first results, now 3 years old, on the major rock-forming elements, magnesium, aluminum, and calcium, are shown here, ratioed to silicon. And what these results showed, you're looking at the red symbols are from Mercury, the green symbols are from the Earth's moon, and the yellow symbols are a variety of types of rocks from the Earth. Superficially, Mercury has a heavily cratered surface that looks a lot like that of the moon, but chemically it is not at all like the moon. And compared with even the other major planets, including the Earth, Mercury is more rich in magnesium relative to silicon and poorer in aluminum and calcium compared with the moon, Mars, and Earth. So that's our first measure that Mercury is something different. We made a lot more measurements after that. All of these measurements, by the way, were made from times when the sun was very active and producing energetic X-rays. And so we waited for more flares to produce more X-rays, and you see the footprints on the surface of the planet that allowed us to build up a larger data set. This is now a fairly recent compilation of similar data that all say this same pattern. Mercury is not the moon, it's not the Earth, it's not Mars in terms of major elements. It is similar to some rocks of the Earth that are high in magnesium, fairly rare as examples on the Earth's surface, but common on Mercury. And now we're even mapping all of these quantities. Here's a map of magnesium silicon showing you that there are important variations, some of which can be correlated with geological maps made on the basis of morphological features about shapes and superposition. Some are geochemical boundaries that don't have obvious geological boundaries. So that's turning out to be interesting. But here are some unusual results. Mercury, remember, is mostly iron. We know from the mean density, but iron is very rare at the surface. The surface abundance of iron is 1 to 2%, and that's low by many multiples compared to the other inner planets, compared even to the moon. Mercury has less iron at its surface and more iron in its core than any other body. And so the ratio of iron metal to iron in rock is much higher on Mercury than on any other body. And that is satisfied by a condition that the chemists call chemical reduction, that compared with the other terrestrial planets, Mercury is chemically more reduced than Earth, than Mars, even than the moon. And most of the iron, which is the most abundant element, is present in the most reduced form, iron metal. But let's look at the volatiles. The very first surprise was this one from the X-ray spectrometer. This is a map, this is a plot of the abundance of sulfur versus calcium. And you know that calcium is lower than other terrestrial planets, but sulfur is high. It also seems to correlate with the calcium. But the sulfur abundance on Mercury, and sulfur is one of those moderately volatile elements that should be removed by high temperatures. Sulfur is more abundant on Mercury than on the Earth by a factor of about 10. All the theories said it should be absent, and there it is. There are more volatile elements that are there in abundance greater than are predicted. This is a plot of potassium on one axis versus thorium on the other. It comes out of the gamma ray spectrometer. Both of these are radioactive elements. Potassium is a moderately volatile element, and thorium is not. And the ratio of potassium to thorium for Mars and the Earth falls along this line. This is the line for the moon, these blue symbols, and Mercury's here in red on the same line as the Earth and Mars. So compared to the other inner planets, potassium, this moderately volatile element, is in proportion to thorium with the same ratio that it is for Earth and Mars. And the Moon, which is known to be depleted in volatile elements, looks very different. So again, in this element, an alkaline metal, Mercury defies the predictions of the theories for how Mercury was assembled. I'll show you just one more plot. This has not been published, and that's chlorine. Chlorine is a volatile element, even more volatile than potassium. It's plotted here on the vertical axis versus potassium here, and you see ratios as these lines of slope 1. This upper line contains Mars and some meteorite classes that are rich in volatile materials. And these blue symbols with error bars are the measurements for Mercury. Earth is lower down with a lower chlorine-potassium ratio than Mars or these meteorites. So here again, Mercury is not volatile deficient. It has more of this particular volatile, or this ratio of volatiles, than even the Earth's surface materials. So the theories are not right. It means that by whatever processes the inner planets were assembled, it is possible to make a planet that is both rich in iron metal and not depleted in volatiles. And so this list of ideas here, that there was a giant impact, that the solar nebula was very hot in the vicinity of the region where Mercury assembled or differentiated, or that Mercury was preferentially produced by material that was solid only at the highest temperatures in that solar nebula, can all be rejected. And we're back to the drawing board on ideas for how the inner planets were assembled in a way that allows a Mercury to be an outcome of that process. It does point to more reduced starting conditions for the material from which Mercury was assembled than the other inner planets. So we know that there are some conditions in the solar nebula that varied with position. But the theoreticians are now at work attempting to reconcile these new measurements with everything else we know about the solar system. Let me talk for a few minutes about the magnetic field. Mercury, the Earth, you probably know, has a magnetic field. It's the reason we can navigate with compasses. The magnetic field generates a volume of space known as the magnetosphere that shields the surface of the planet from much of the dangerous radiation that comes from the sun, that comes from other parts of the galaxy. Without the magnetic field, this would be a higher radiation environment, one that would be more of a challenge to the origin and evolution of life. Mars and Venus do not have modern magnetic fields, but Mariner 10 discovered that Mercury does. That's a little odd because we think the Earth's magnetic field arises from convective motions in the fluid outer iron-rich core by a process known as the magnetic dynamo. It's a process that converts rotational energy of a convecting fluid into electromagnetic energy and produces a sustained magnetic field. And we know a great deal about the characteristics of the Earth's magnetic field, but what's key is that there be some energy source to drive those motions in the core, and the core has to stay fluid for the age of the planet in order for there to be a magnetic field today. So Mercury is a much smaller planet than Earth, but it has a modern magnetic field. And so we wanted to learn enough about the magnetic field to try to understand a little bit more about its geometry and its history. So the geometry was a bit of a challenge. The field of Mercury is weak. It is an Earth-like field in its geometry, but it's weaker by a factor of 1,000 by one measure, the dipole strength. And it's close to the sun, so that the volume of space dominated by Mercury's magnetic field is very small. And what that means is that there are current systems in magnetospheres around planets. We have them at the Earth. At Mercury, those current systems are very close to the planet. And so measuring the internal magnetic field is a challenge to separate out the fields associated with those external currents. And in particular, a lot of the analysis techniques used for planetary magnetism don't work. But a measurement is depicted here on these slides that was a surprise. We made measurements of the location of the magnetic equator from the position at which the magnetic field attributable to the planet's interior was parallel to the spin axis, as it should be at the equator. And we did that for all orbits as a function of longitude. And you see the first plots as a function of longitude here. So this is the geographic equator at the bottom. This is the position of the magnetic equator. This is longitude on the horizontal axis. And the answer is that the magnetic equator is offset from the geographic equator at all longitudes by about 500 kilometers on this plot, or this plot. And this is a small planet. That's about 20% of the radius of the planet. So this looks like the Earth's magnetic field, but unlike the Earth, where the magnetic field is at the center of the planet, this magnetic field is offset by 20% of the radius toward the North Pole. So it looks like the field of a bar magnet, the so-called dipole. The dipole points in the same direction as the field on the Earth, toward the South Pole of the Earth. It's aligned with the spin axis, as the Earth's field is if you average over enough time, but it's not at the center of the planet. It's offset. And that means that the field is asymmetric about the equator. It's stronger at the North Pole than the South. It means that magnetic field lines that are open to the magnetosphere and the solar wind intersect the planet over a larger area in the south than the north. We don't know very much about the history of this field up to now. All we know is the field that was measured by Mariner 10, which visited 40 years ago, and the field that we can measure today, and those are indistinguishable. So Messenger has been looking for the 3.5 years we've been in orbit for evidence of an ancient field. On Mars, on the Moon, on the Earth, the evidence of that ancient field is found from rocks permanently magnetized in the crust. So we've been looking for evidence of magnetic anomalies in the crust of Mercury. And I'm going to show you some new results that no scientific audience outside of our team has yet seen, though that will change next week. Before I do that, I want to say something about our orbit. There are two plots on this diagram. Ignore the simple one and look at the complicated one. It is the distance that the spacecraft is from the surface, the so-called periapsis altitude, versus time. And time begins on the left about 2 years ago, and it extends over to the right to next March. And what you see is that the distance of closest approach gets lower and lower and lower with every orbit, except there are a few places where it jumps straight up. And that's where we have enough propellant to fire our thrusters and raise the altitude of closest approach. But we're running out of propellant. I'll come to that in a minute. But notice the numbers here. Prior to last spring, we never got closer to the planet than 200 kilometers. And prior to this summer, we never got closer than 100. But starting this fall, we got closer than 50. And we got down as close to 25 twice. And when we crossed that distance of 50 kilometers, we suddenly saw something we hadn't seen before. We saw crustal magnetic anomalies. And what you see on the top is a measurement of the magnetic field magnitude. And what you see in the middle plot is a residual. After you correct for the internal field, after you correct for the magnetospheric fields, and after you correct for the long wavelength component of the observations. And what's left is a shorter wavelength set of anomalies, these things here. And what we have shown is these anomalies persist from orbit to orbit. Here's the next orbit. And they're repeatable if we fly over the same terrain, as long as we're substantially closer than about 50 kilometers to the surface. And we can begin to map them and compare them to the geology, and there are places that have magnetic anomalies. There are places where we cannot measure a magnetic anomaly, but for the first time, we are looking at magnetized portions of the crust dating back to a time when the impact flux was very high, maybe 4 billion years ago. and Mercury had a magnetic field. And so we can conclude several things. We conclude that even under the very reducing conditions that Mercury, under which Mercury was assembled, even given its very low iron content, it has minerals that are capable of permanent magnetization. And that magnetization was acquired in crust that's as much as 4 billion years old. So it changes our baseline for understanding the history of the magnetic field from 40 years, the time since Mariner 10, to 4 billion years. So that's a factor of 10 to the 8th in an improvement in our understanding. Let me close with a discussion of Mercury's polar deposits. John alluded to that in the introduction. It's a story that is still continuing, so I'll show you some brand new results. But it goes back 20 years to Earth-based radar, which documented the fact that there are deposits on Mercury that look like water ice to a radar system. They reflect the radar waves, they depolarize the radar waves the same way that water ice does at the poles of Mars and on the icy satellites of Jupiter. And the reason that's not crazy, despite the fact that at the equator of Mercury, the difference in temperature between day and night is 600 degrees centigrade, the reason it's not crazy is that Mercury's spin axis, unlike that of the Earth, has almost no tilt. It's perpendicular to its orbital plane to within 2 minutes of arc, which means that an impact crater, a hole in the ground, at the poles is in permanent shadow. There's not much atmosphere. A hole in the ground is looking at empty space, and it's extraordinarily cold, cold enough to preserve water ice. So the hypothesis going back 20 years was that we would find water ice at the poles of Mercury. But all we had were these radar images. So we took several experiments that one by one helped us confirm this 20-year-old hypothesis. The first was simply to ask, are all the polar deposits in areas of permanent shadow? Because when the radar images were acquired, we hadn't seen more than half the surface. Mariner 10 had only imaged 45% of the surface. So we didn't know whether all the radar deposits were in impact craters, much less in areas of permanent shadow. But we could make systematic measurements of sunlight over the course of a Mercury solar day. You're looking at the South Pole and a sequence of images taken of just where the sun is shining over the course of a complete solar day, which on Mercury is 6 months long. And from that, we could make contour maps of how much sun falls on any given part of the South Polar region. This is the South Polar region, and all those black areas never see the sun. And unlike planets like Mars, the spin axis of Mercury is stabilized by a resonant state between its spin, its rotation, and its trips around the sun. And as a result, the spin axis is extraordinarily stable. And so if something is in permanent shadow for 6 months, it's in permanent shadow for 3 or 4 billion years. So those areas in black are truly in permanent shadow, and we can compare them with the areas that show up in the radar images, and they compare very well. All of the areas that are bright in the radar images are in areas of permanent shadow, as documented directly by imaging of the surface. Then there's the question of what are the polar deposits made out of? So we took a neutron spectrometer with us on the spacecraft specifically to answer this question. Remember that the planet is bathed in neutrons because they are produced by cosmic rays. But some neutrons are absorbed by materials at the surface, and the best absorber of neutrons over most energies is the hydrogen atom. And so the neutron flux has long been used as a tool to look for hydrogen, or H2O, in the case of water ice. And here you see measurements in red. This is an intermediate range of neutrons compared against two models, a black model in which the polar deposits have no water ice, and a blue model in which the polar deposits are pure water ice. And you see a good match to the blue model. The story is complicated because we have also measures of higher energy neutrons. There are fewer of them. The error bars are larger. But again, the black curve shows you what would happen if the polar deposits had no water ice for neutrons of this energy. The blue shows you what it would be if they were pure water ice, all the way to the surface for neutrons of this energy, and the red data split the difference as you go toward the pole, toward the right. So the way to fit both kinds of data is to say that the polar deposits are water ice, but that in most locations they're covered with a thin layer, 20, 30 centimeters thick, of something that doesn't have much hydrogen. And that's enough to slow down the fast neutrons and not the intermediate energy neutrons, and explain both data sets. We had another instrument, and that is the laser altimeter that we use to do measurements of topography. But it's also an active reflectometer. And you see on these slides a map of the average reflectance of the surface at the wavelength of the laser. And for most, there's an area in gray where we didn't look at first because the orbit of the spacecraft didn't take us right over the North Pole. And so there's a cutout where we had no data. But in the rest of the terrain, the average reflectance is shown kind of in yellow-green, and there's a number there on the slide. And the areas where the polar deposits were seen with Earth-based radar show up very dark. They're half the reflectance of the average for Mercury, which itself is very dark. So there is a signature in the reflectance of the surface. These are the areas where the neutron spectrometer told us that there's a cover 20 to 30 centimeters thick of non-hydrogen bearing material. That material is very dark. It's darker than the rest of Mercury. It is not Mercury soil. It is something special and very dark. Then we tilted our spacecraft and used our laser to look at craters that were even farther north. Then we were getting closer and closer to the North Pole. And what you see in this plot, it's somewhat complicated, is that there are places where the reflectance is greater than the average for the planet by factors of 3 or 4, namely in the floor of that crater. That crater is called Prokofiev, and I want to show you some brand new results that were published just this month, where we took direct images of the permanently shadowed region of the cratered floor. Sorry, I went the wrong way. Here's the crater Prokofiev. This area to the south is in permanent shadow, but it's obviously an impact crater, and you can see a lot of detail in the floor. And this is itself a mosaic of several images under different lighting conditions. The yellow shows you where Earth-based radar says the polar deposits are located. Indeed, they are in areas of permanent shadow. This is a contour map of where the laser shows you the high reflectance areas are. And in this particular plot, we changed the color scale high as red. So this area where there are polar deposits is high in reflectance in this crater, not dark. Under these conditions, we opened our broadest filter on our imaging system, made a long exposure image to look into the areas of permanent shadow. There is no direct sunlight falling on the surface in the areas of permanent shadow, but there is reflected light off the crater walls and off the central peak, enough to see. And what you see is this. And I draw your attention to this boundary here, between brighter terrain here and darker terrain out here. This is within the area of permanent shadow. It coincides with the mapped areas of permanent shadow. More importantly, it has sharp boundaries. It shows you very small features, including small impact craters. The reflectance of the surface doesn't change as you go across these small craters, some of which must be very young to have survived. And the implication is that whatever is making this surface very bright is young. Either it was recently deposited or it is steadily deposited on top of surfaces containing some very young craters. It coincides with the area mapped with radar imaging. So we're now building up images of these craters with direct imaging at visible wavelengths to combine with the laser reflectance measurements of reflectivity and the neutron spectrometer measurements to put together a picture of what we're looking at. But here's the hypothesis, that in areas of permanent shadow near the North Pole, to the left in this image, these are places where you can collect material that impacts Mercury in the form of a comet or a volatile-rich asteroid. So this cartoon imagines that a comet is impacting the surface. A comet is classically known as a dirty snowball, as described by Fred Whipple more than half a century ago. Mostly ice, but with other material, some of which is dark. Some fraction of that material, after it is vaporized on impact, bounces around in Mercury's gravity field, finds its way to high-latitude craters where it is frozen in place, because these are some of the coldest places on the planet. But remember that not all this crater is equally cold, and so the higher temperature areas lose their ice. And more importantly, they also lose this dark material. And we don't know what this dark material is, but we know it's a volatile. That is to say, it is removed by high temperatures. It is removed only by temperatures that are higher by 50 or 60 degrees than ice itself. So that tells us something specific about the material. But it is extraordinarily dark. It is among the darkest material in the solar system. And if it is delivered by comets, in the same manner that we think the ice is delivered, then the leading candidate for this dark material is something carbonaceous. This dark material coats all of these small solid objects of the outer solar system, where the amount of reflected light coming off of these objects is measured in a few percent. You can count it out on your fingers. They're spectrally red, and they're best matched on the basis of laboratory measurements with complex macromolecular organic stuff. Tar, tholin is a fancy name. And that material fits what limited we know about this dark material on Mercury. It could be delivered by the same objects that deliver water ice. It has the right reflectance, and it would be volatilized at about the right temperatures. But we have no direct chemical measurements. Anyway, by this hypothesis, further removal under temperature leads to what the sedimentologists on Earth calls a lag deposit of dark material that, except in the coldest areas, leaves this layer, 20, 30 centimeters thick, of very dark material overlying and thermally protecting the underlying water ice. So the water ice shows up in radar, it shows up in reflectance measurements in the few places that are extraordinarily cold and the ice is stable at the surface, and the rest of the time the deposits look very dark. So let me wrap up by saying that just asking these three questions out of many we could have asked about Mercury has taught us a lot about the innermost planet and something about our own. We learned that all of the models proposed for how to make an Earth-like planet end up as metal-rich as Mercury have to be cast aside, because they made predictions in the proper scientific method that were testable, and those tests have shown that the predictions are not correct. Namely, the prediction was that Mercury should be depleted in elements as volatile as sulfur and potassium and chlorine. It is not. So that changes our ideas for how the inner planets were formed. And we are still awaiting a generalized theory for inner planet formation that can account both for the variations in major elements among the planets and the variations in volatiles. We've learned something about Mercury's magnetic field, the only other example in the inner solar system beyond Earth of a planet with a modern magnetic field. We learned that you can have a magnetic field in an otherwise Earth-like core, we think, that is very asymmetric about the equator, that does not look like the centered dipole that describes the Earth's modern field and has been assumed to describe the Earth's magnetic field over its entire history. So what if the field we see today at Mercury describes some past state of the Earth's magnetic field? It would mean that we would have to rethink our interpretation of paleomagnetic data on the Earth. And finally, we've seen this view of Mercury's polar deposits, first seen by Earth-based radar 20 years ago, and hypothesized then to consist of water ice. And we assembled a suite of instruments to test that hypothesis, and that hypothesis passed. The polar deposits are indeed mostly water ice on the basis of neutron spectrometry, on the basis of detailed thermal models that I didn't describe here that make use of measured topography, on the basis of the permanent shadowing, on the basis of the reflection measured actively from lasers in the coldest spots where water ice is predicted to be stable right at the surface. But we discovered something new, that these deposits are covered not with Mercury soil to keep them cold, but with something different, something darker, something volatile, something possibly carbonaceous. So here we have an example where the planet closest to the sun, the planet that experiences the greatest range in temperature from day to night, the planet where we least expected to find it, is a witness plate for the delivery of ice and probably organic material from the outer solar system, a process probably that went on over the whole history of the solar system that may have contributed to the early evolution of organic chemistry on our own planet. We're not recording all of that history here on Mercury. We're seeing only the most recent tens of millions of years. But should we go back with the right tools, we could sample this set of deposits that's telling us about how water and organic material were delivered to the inner solar system throughout the history of our own planet. I'm just going to close with this one last, still complicated slide to show you what's ahead for the next 4 months. This is another one of these plots of distance of closest approach to the planet. Only this one only goes from next January to next April. And because of the cleverness of our propulsion engineers, we have a little more propellant remaining after our last scheduled maneuver, which was to have taken place next January, next month. Enough to do what they call a set of hovering maneuvers, starting in March and continuing for as much as 2 months, that will keep us, as the planet rotates underneath us, in orbits where the closest approach is about 15 kilometers off the surface. We've never been that close. So we will be taking magnetic field data. We will be taking images at unprecedented resolution. We'll be making geochemical measurements on the scale of geological units really for the first time at that scale. So we hope to have a few more discoveries in our pocket before the mission ends. Anyway, I hope you will agree with me that there are reasons to explore the solar system and to explore Mercury in particular, and some of those reasons do inform our understanding of our own planet. Thank you.
We do have time for a few questions. There are microphones on both aisles, so if you would like to ask a question of Professor Solomon, he's ready to answer, and when we finish, there will be a reception to follow, and you're all invited. Over here.
Is it fair to say that there's little evidence that Mercury had a global magma ocean?
That is a fair statement. Some context for the rest of you folks. The late stages of accretion of the inner planets are energetic events where there are larger and larger impacting bodies as the number of objects in the inner solar system goes from a large number of small objects to a much smaller number of large objects. And the leading idea for the explanation, leading idea to explain the origin of Earth's moon is that Earth was hit by an impactor about the size of Mars some tens of millions of years after the formation of the Earth. That was a major event in the history of the Earth. It led to ejection of a lot of material in Earth orbit. Some of that material accreted to form the moon. Mercury ended up with a lot less silicate than metal compared to the other planets. And so the question is whether there was a giant impact that was responsible for some of that. If the giant impact would have removed the volatiles, I think one can reject that idea. The theoreticians who are looking at giant impacts on Mercury and reaccretion of material are exploring whether there are possibilities for retaining enough of the volatiles to account for our measurements. So I think the jury's still out as to whether there was a giant impact on Mercury. A giant impact would have melted a substantial fraction of the planet. In the absence of a high iron content, we would not see the evidence of a magma ocean in the crustal composition that we see on the Earth and Moon. So the absence of evidence is not necessarily an argument for the absence of the phenomenon. But the way you cast the statement was still correct. We don't know that there was a magma ocean, but it's hard to disprove it.
Yes.
Is it possible to very roughly estimate the expected comet impact rate on Mercury and the expected volume of those ice deposits to try and understand how much ice we can expect comets in general to deposit on a planet?
Yes, it is. I don't have those in my frontal lobe, but we do know the population of comet orbits. We know that there are comets that pass inside the orbit of Mercury. Some of them are sun grazers that get to the upper atmosphere of the sun. A few of you may have heard of Ison, which was a comet last year that got so close to the sun that it didn't survive the passage. But that was well inside the orbit of Mercury, and by the way, flew by Mercury close enough that we could take data. So there are comets that have a range of orbits, and one can calculate, based on the current population of comets, what the impact rate should be on any solar system object. All of the periodic comets are thought to have originated farther out in the solar system and been kicked in by passage of some neighboring body. And those kinds of events are stochastic. It's harder to go back over all of solar system history and know with confidence what the rates are. But to answer the question implied by your actual question, the impact rates of comets on Mercury are sufficient to supply over geologically recent time the volume of water ice that we see.
Sean Solomon, thank you very much for a wonderful evening. Great lecture. You're all invited to the reception as well.
If I can say one more thing, it is that if we send a university administrator on a quick trip to escape the Earth, don't go to Mercury. There are more hospitable places than that. Thank you, John.
Shall do the science test, no? Try one of these tests in case.